Hey everyone, in this video we're going to talk about section 4.4, complex zeros of polynomial functions. And we are joined by our co-host today, Mason Bean, but he's pretty tired, so I'll let you know if he does anything of importance today. So we've been studying polynomial graph theory. This lesson is going to extend our understanding of zeros of polynomial functions. In our last lesson, we learned that the fundamental theorem of algebra tells us that a polynomial of degree n has n roots. Well, a stronger form of this is that a polynomial function of degree n greater than or equal to, or greater than 0 has n complex roots. Okay, and so some of those zeros may be repeated. So this should make sense to us. Like, let's say that we have a fourth degree polynomial. Well, we know that some fourth degree polynomials have 4 roots, 1, 2, 3, 4. But we've also seen this where a fourth degree polynomial only has 2 roots that show up on the graph, right? Like, we've seen that before. Well, it still has 4 roots, just we only have 2 of them that are showing up on the graph because these are our 2 real roots. The other 2 roots are going to be complex numbers, and complex numbers do not show up on the real coordinate plane because our coordinate plane only graphs real numbers. So remember, complex numbers are going to be written in the form a plus or minus bi. And really, all real numbers are complex numbers, just our b term happens to equal 0. So like, let's say, for instance, that I have a number 3. Well, I can turn that into a complex number by adding 0i to it, okay? So in our last lesson, we also learned about a bunch of different equivalent statements of ways that we can talk about zeros. 3 of these are going to be true when we're talking about complex zeros of polynomial functions. So the first one, x equals k is a solution or root of the equation f of x equals 0. Okay, that's true. 2, k is a 0 of the function f. 3, x minus k is a factor of f of x. Last time we talked about having 4 fundamental connections. Which one's missing? Flip back in your notebook and go ahead and check and see which one we're missing. The one that we're missing is that k0 is a point on the graph. Okay, and let's think about why. If a 0 has an imaginary component, like let's say for instance my 0 is 3 plus, well, let's not do 0i, 3 plus maybe 2i. Okay, if it has an imaginary component, it can't be graphed on the real number plane because our real number plane only has real numbers as our x's and real numbers on the y's. So it's not going to show up on that graph. Okay, so that's the fourth one that we're not going to have if we have imaginary roots. So we also have a complex conjugate for zeros. Okay, so like for instance, if we have 3 plus 2i, we're immediately also going to have 3 minus 2i. Okay, and let's think about why that is. Well, it kind of has to go back to where we generate imaginary numbers, right? Where do they come from? Well, it takes a square root to generate I, right? And how do we generate I? Well, that's going to be the square root of -1, right? And so that's going to be I. So remember, when we take the square root of something, we can also have plus or minus. So let me write that down. So like, for instance, let's say that I have, hold on, let's say for instance that I have -4. Okay, well, if I'm going to take the square root of that, that could be, well, no. Let's see. Let's say that I have x equals -4. Okay, x squared. If I take the square root of that, well, that could be plus or minus 2i. Okay, so that's where that plus or minus comes from. We're going to have those pairs. So let's take a look at some examples. So first we're going to write the polynomial in standard form, and then we're going to identify the zeros of the function and the x-intercepts of the graph. Okay, so our function, we have 2x minus 3 times the quantity x minus the square root of 5i times x plus the square root of 5i. Identifying our zeros of our function, that's going to come from setting our function equal to 0, and then finding all those values of x that are going to make that 0. So we'd have 2x minus 3 equals 0. We'd have x minus square root of 5i equals 0. And then x plus square root of 5i equals 0. So solving for each of those, let's see, this one's going to give us x equals 3 over 2. That's a 0. We have x equals, if I add that over, we're going to have the square root of 5i. And then we'll have x equals negative square root of 5i. Okay, so here are our zeros. Now, if we're thinking x-intercepts on the graph, only one of them is going to show up, and that's going to be our real number 1. Okay, so we have an x-intercept of 3/2, 0. Okay, so we have 3 zeros, but I only actually end up having one x-intercept because that's only going to be the real component. All right, okay, so next up we're going to write our polynomial in standard form. So to do this, we're going to have to distribute everything and then combine our like terms. So whenever we have complex number portion of this, one thing that I like to do is I like to worry about the complex numbers first and then worry about multiplying in the real number factors as well. So let's start with this, okay? So just like we normally would do, we're going to double distribute. So let's see. So I'll have my 2x minus 3 over here. And then let's see. So x times x is x squared. X times square root of 5i is going to be plus x square root of 5i. Then I'll have minus x square root of 5i. And then, let's see, I will have minus, then the quantity square root of 5i squared. Right, because I have one of these terms times another one of those terms, and those terms are the same, so I can just do the quantity squared. All right, let's see what we can simplify from here. So I see that my two middle terms, my x square root of 5i's, I have a positive version, I have a negative version, so those are going to condense down. That's good news. And then next up, let's worry about this thing. Okay, so I know that I have this quantity squared, so this means that I'm going to be able to, just off to the side, I can distribute my exponent of 2 to each one because they're multiplication connecting those two together. So that'll be the square root of 5 squared times I squared. Well, the square root of 5 squared is just going to be 5. But now, let's see, what is I squared? Well, our imaginary number comes from taking the square root of -1. So what happens when that's equal to I, okay? What happens when I square I? Well, I'm going to square the square root of -1, so I squared is just going to be equal to -1. So this will be multiplied by -1. So right now, I have my x squared left over, and then I will have minus 5 times -1, which 2x minus 3, that'll be x squared plus 5. Okay. Let's keep going. So we've dealt with everything. I see that I don't have any imaginary numbers left, which is good. That's exactly what we want. So now we can just distribute this. So continuing on, let's see, we'll have 2x cubed. We'll have plus 10x. We'll have minus 3x squared, and then minus 15. So writing in standard form, we should have, let's see, 2x cubed minus 3x squared plus 10x minus 15. There we go. Okay. Flipping over our page, we're going to go into the next example. So for our next example, we're going to write a polynomial function of minimum degree in with real number coefficients whose zeros include those listed, and we can leave in factored form. Okay, so we're given 2 zeros. We're given 3, and then we're given 2 minus 5i. Well, the good news is that if we're given this complex root, we also automatically get another one. Okay, so we also will automatically get 2 plus 5i. It's complex conjugate. Okay, so we have 3 zeros. I have x equals 3. I have x equals 2 minus 5i. And I have x equals 2 plus 5i. So if I want to turn these into factors, I just need to go backwards from what we did before, like here. Okay, we had the factors and we set them equal to 0 to solve for the roots, or to solve for the zeros. Now we're just going to do that backwards. Okay, so I'm going to set these equal to 0. So this will be x minus 3 equals 0. This will be x minus 2 plus 5i equals 0, and this one will be x minus 2 minus 5i equals 0. Okay, so these here are going to be my 3 factors. So my function f of x will be equal to, my first factor can be x minus 3 my second factor can be x minus 2 plus 5i, and then I can have x minus 2 minus 5i. Okay, let's see. It says that we can leave in factored form, but I'm going to actually encourage you to go ahead and pause that video to try turning it into standard form. Okay, so go ahead, pause the video, try standard form. All right, hopefully you've had a chance to try that out. Let's go ahead and check our answers. So when we're going ahead and distributing our complex roots together, we do have to do kind of a triple distribution there. So the good thing and the good news is that our imaginary components should all either add to 0, or we're going to end up with an I squared, which is going to end up being -1. Okay, so we shouldn't have any imaginary numbers left after we multiply our two complex roots together. For our final answer, I got x cubed minus 7x squared plus 41x minus 87. So go ahead and check your work in comparison to mine. If you think I made a mistake, let me know, so that way I can go back and change the video for next year, okay? Right now our co-host is building what I like to call a nest. Very important work, probably more important than the work we're doing today in our video, but just wanted to update you on his current whereabouts. All right. Going on to example 3, so we're going to find all of the zeros and then write a linear factorization of the function. And as a hint, this is a fundamental theorem of algebra problem. So let's see what we have. We have a function 6x to the 4th minus x cubed plus 32x squared minus 52x minus 21. Okay, so for this example, we start with our polynomial. We're going to end up using synthetic division to figure out some of our roots and then continue going on from there. Well, we're not given any roots to start with. So this is where we're going to have to go to our graphing calculator, and we're going to have to graph this function and then see what roots we have. So go ahead and graph that out. So pulling it up on Desmos, I went ahead and I graphed our function, and I see that we have two roots, okay? So I have one root at -0.333, okay? Well, that's going to be -1/3. And then I have another root at 1.5, which is going to be 3/2. So I see that I have two roots, but since this is a 4th degree polynomial, I do know that this polynomial is going to have 4 roots. So that means that we only see 2 of them on the graph, and zooming out, yep, not like it's not in our window. That means that 2 of them are going to end up being complex numbers, okay? So coming back over here, we do know we have real zeros. X equals -1/3 and x equals 3/2. So starting off with this, let's go ahead and use synthetic division to be able to start reducing this down. It doesn't matter which zero we start with, so we can either start with the -1/3 or the 3/2. I'm gonna go ahead. I'm gonna start with the -1/3 though. So -1/3. Here we go. So synthetic division, we'll write our coefficients. So 6, -1, 32, -52, and -21. Making sure we didn't skip any terms. I think we're okay. Okay, here we go. Bringing down our 6. So 6 times -1/3 is -2. Adding those together is -3. -3 times -1/3 is 1. Adding those together is 33. -33 times -1/3 is -11. Adding those together is -63. Times -1/3 is 21. Adding those together is 0. Sweet. So we've reduced it once. I still think that if this would be our x cubed term, this would be our x squared term, this is x, and this is our, that term. So not enough to factor, so we're gonna have to do synthetic division another time. So here we go. So using 3/2 this time, we shall repeat. So bringing down our 6. 6 times 3/2 is, let's see, 18/2, 9. Adding those together is 6. That'll be 9 again, which will be 42. let's see, 42 times 3 halves is 63. And then adding those together is 0. Sweet. Okay, so now we have this as 6x squared plus 6x plus 42. Excuse me. Okay, so we're going to go ahead and try to factor this if possible, because we're going to set this equal to 0 so we can find our other roots. So one thing, I see that our coefficients 6, 6, and 42, I think all of those are divisible by 6. So if I pull a 6 out, I'm going to have x squared plus x plus 7. So looking at what we have left here, trying to factor that, well, we have x squared plus x plus 7. I don't think that factors, okay? And to us, that should make sense. Why is this not going to factor? Well, remember, when we ended up looking at our graph, the two zeros that we had were given to us, right? We had the negative 1/3 and the 3 halves. So that means that the remaining zeros that we have are going to be complex. Well, complex numbers don't come from being able to factor, okay? So that means that since this does not factor, we have to use the quadratic formula. And for those of you out there who are big quadratic formula fans, this is for you. So here we go. No, I took out that 6 there. Our answers, if we did not take out that 6, might look a little bit different. Since we already factored that out, though, we'll just have to remember to include that later on. So here we go. So we'll have x equals negative b is 1, so negative 1 plus or minus the square root of b squared, so 1 squared, minus 4 times a, which is 1, times c, which is 7, and that's all over 2 times a, which is 1. All right, continuing on. So let's see. We have negative 1 plus or minus the square root. 1 squared is 1 minus 28 all over 2. So we have negative 1 plus or minus the square root of negative 27 over 2. Okay, from here, now we're going to take a look at our radical, and we're going to think, okay, can I simplify that radical? So if I were just pretending that this is the square root of 27, well, I know that's going to be equal to the square root of 9 times 3, which is equal to 3 square root of 3. So I'm going to rewrite this as negative 1 plus or minus. Well, remember that we also had that negative 1 there. Let's talk about that now. Okay, so we had a negative 1. So this is really times a negative 1 times a negative 1 underneath that radical. Well, I know that I can pull out that negative 1 by calling it I. So this will be 3i square root of 3. That is all over 2. So looking at this, here's another reason where we get that plus or minus. Look, that plus or minus comes from that quadratic formula. So that's where we can see that we have our complex conjugate there. So our zeros, sorry, I have like something in my throat. We have x equals negative 1 plus 3i squared 3 over 2. We have x equals negative 1 minus 3i squared root of 3 over 2. And then we had our 2 zeros from up above. So we have x equals negative 1/3, and then x equals 3 halves. So here are all of our zeros, but I do believe that the instructions told us that we want to find the linear factorization of the function. So that basically just means that we want to write it in factored form. So f of x will be equal to, now, here's the deal. This is something that we always seem to forget, and it's almost one of the most important parts. When we did synthetic division, all along our leading coefficient was, 6, right? We pulled out that 6 in front of here before we did the quadratic formula. Since we pulled out that 6, that's going to be our leading coefficient that we're going to need to have. So our 6 isn't incorporated in any of the other factors from these zeros that we have, so we need to make sure that we add that 6 back in. So we'll have 6, and then, let's see, we'll have x plus 1/3. We can have x minus 3 halves. We're going to have x, and then here, depending on how we want to write this, I might just write this as x minus negative 1 plus 3i square root of 3 over 2. And then x minus negative 1 minus 3i square root of 3 over 2. And I'm perfectly content for us to leave that, so don't feel like we need to be able to change any of those. We can leave it just like this, okay? So here is our linear factorization. All right, looking at example 4, it's just like example 3, very similar, okay? So I want you to go ahead and try out example 4 on your own, and then be prepared to bring what you got into class, and then we can go over and talk about what it is that you found, okay? I think we're going to stop there because example 5 and example 6 are going to give us one of the zeros. They're going to give us one of the complex zeros, and so we're going to have to go through and find all of the other ones and then write a linear factorization. There's 2 ways that we can do it in class. I think that we'll talk about those in class it's better in class to do those questions. Okay, let's just leave it at that. All right, that's all we have for this video, so I will see you all later.